Lee from Carnegie Mellon.
Hi. Today I'm going to talk about leveraging input and output structures for joint mapping of epistatic and marginal eQTLs. I'm Seunghak Lee, and this is joint work with my advisor, Eric Shing. First, let me start with a brief introduction of the genome-wide association mapping. The goal of the genome-wide association mapping is to find SNPs which are associated with observed traits, which include gene expression traits and disease status. Let me explain this idea with a graphical representation. Here we have a set of SNPs, and each node represents a SNP. And we have usually order 1 million SNPs. And also we have a set of genes, and each gene represents a gene, and we have order 1,000 genes. And if we represent association between a set of SNPs and a set of genes by edges, then the goal of the genome-wide association mapping is to find the edges between these two sets of between the set of SNPs and the set of genes. However, this problem is extremely difficult. The main difficulty is here. The number of samples is much smaller than number of SNPs. Usually we have number of SNPs order of 1 million, and we have number of samples order of 1,000. And also there exist other confounders, which include complex genetic architecture, population structures, and environmental factors. So to increase statistical power, it is desirable to use prior biological knowledge. And there have been a lot of work in this line of research. For example, graph-guided fused Lasso incorporated trait networks for GY inference, and also LearnNet uses annotations in genome, such as conservation scores and the locations of the transcription factor binding sites for better search of association SNPs. This is the outline of this talk. First, I'm going to define the problem, and then I'm going to tell you some backgrounds of this work, and then I will propose our methods, and the experiments and conclusions will be followed. Let me start with the input and output for GWA mapping algorithms. For the input, we need two sets of matrices. The first matrix is gene expression levels of n individuals. And the second matrix is the SNPs for the same n individuals. And here are the examples of the Y and X. And output of the algorithms is going to be this, matrix B, which represents the associations between SNP matrix X and gene expression matrix Y. So here, the element in this matrix B is going to be like this. So the element at the kth row and the jth column is going to be the effect size of the jth SNP on the expression levels of the kth gene. So it means that if this value is 0, there's no association between the jth SNP and the kth gene. And now let me move on to the model that I'm going to use for the following algorithms. I'm going to use a linear model, which is represented by this. Here we have output variable y. It means that it represents the expression level of the kth gene for ith individual. And we have also input variables, which are j SNPs for for the same individual. So xji represents the jth SNP for ith individual. And also we have regression coefficients, beta, which represents the effect size of the jth SNP on the kth gene. So you can think of this linear model as follows. This output variable is actually the linear combination of the j SNPs weighted by the regression coefficients matrix, j regression coefficients. And if you represent this with a matrix format, it looks like this. Here we have a gene expression level matrix, and we have a regression coefficient matrix B, and this is the SNP matrix, and we have a Gaussian noise. And now let me move on to this problem statement. The problem is as follows. Given X, the SNP matrix X, we want to find the B, the regression coefficient matrix B, that explains Y, which is the gene expression level matrix, as well as possible. So the first method that we can think of is least square method, which is a very beautiful algorithm. We can compute the solution very efficiently. However, unfortunately, least square solution does not work here. The reason is that the number of SNPs is much, much larger than the number of samples. Number of SNPs is, as I mentioned, number of SNPs is order of 1 million, and number of samples is order of 1,000. Now let me tell you some backgrounds of our work. Let me start with a very important assumption, which is the sparsity assumption. This is very important because eQTL mapping problems can be solved under this assumption. Then what is a sparsity assumption? Which is very simple. The regression coefficients matrix B has only a few non-zero elements. So if you think of this assumption with a graphical representation, we have set of SNPs and we have set of genes, and we assume that there exists only a few number of edges between set of SNPs and set of genes. For example, we usually think that the number of edges is less than 100. So under this sparsity assumption, the problem that I mentioned before can be solved. And here is the very famous method called Lasso, which solves the problem that I mentioned under sparsity assumption. Here, this term is the same as the term that we saw for the least squares method, but difference is the second term. This is called R1 penalty, which is sum of absolute values of the elements in the regression coefficients matrix B. And this R1 norm sets many non-significant elements in matrix B to be exactly 0. It means that many SNPs will have no associations, because if this element is 0, it means that there exists no association between jth SNP and kth gene. And Lasso works well even when the number of SNPs is larger than the number of samples under sparsity assumption. And now let me tell you about the property of this method. If we solve this problem, what it really does is as follows. We are going to find the mapping between individual SNPs and individual genes. For example, in this graphical representation, we are going to find the edges between individual SNPs and individual genes. Now let me move on to the group Lasso, which is an extension of the Lasso. It starts with the assumption that we have predefined groups of SNPs. Here the groups of SNPs can be anything. We can group SNPs in the same pathways or gene clusters, and then we can assume that these SNPs in the same group are associated with the same gene expression traits. You can find the groups of SNPs using other prior biological knowledge as well. But here the important point is that we have predefined groups of SNPs. Then we can find groups of SNPs which are associated with gene expression traits using R1 and R2 norm. And here is an example of the R1 R2 norm. Here we have two groups, B1 and B2, and the first group contains 3 members, A, B, C, and the second group contains 2 members, D and E. And R2 norm is defined as follows. And we usually denote this R2 norm by this. And now let me tell you about the property of this R2 norm. If you use this R2 norm, you can enforce the following property. All the members within the group should be or 0 or non-zero jointly. For example, for the first group, we have 3 members. And if we use R2 norm, all the members A, B, C should be all non-zero, or all of the A, B, C members should be 0 together. So there exists such a like grouping effect, grouping behavior if we use R2 norm. I'm not going to go details about of this R2 norm, but the important point is that if you use R2 norm, we can induce this grouping behavior. So based on R2 norm, group lasso was proposed. And this is the same as, it looks very similar to lasso, but difference is here. Instead of using R1 norm, group lasso uses R2 norm with SNP groups. And what this method does is as follows. We assume that we have predefined groups of SNPs like this. And then we are going to find a mapping between groups of SNPs and individual genes. So previously, we looked at mapping between individual SNPs and individual genes. But in this case, we are going to look at the mapping between groups of SNPs and individual genes. The similar idea can be applied to groups of genes. And this model is called Multitask Lasso. And this model also uses R2 norm over here. But in this case, we are going to use gene groups instead of SNP groups. So if we use Multitask Lasso, eventually what we are going to do is as follows. Here we have predefined groups of genes. And then we are going to, if you solve this problem, you can find the mapping between individual SNPs and groups of genes. And again, this actually represents the association between this individual SNP and groups of genes. So now let me move on to our proposed method. Our model is very simple. Our model looks like this. We are going to solve this problem. And our model has 3 penalties. The first penalty is coming from Lasso. And the second penalty is coming from group Lasso. And the third penalty is coming from Multitask Lasso. And this first penalty is going to find individual association SNPs. And the second penalty is going to enforce that SNPs in the same group are selected jointly. And third penalty is going to generate constraints that genes in the same group are mapped to the same SNPs jointly. Basically, these are the effects that we saw in the previous slides. But we are going to do all of this simultaneously. So if you use this model, what we can expect is as follows. Here we have groups of SNPs, and also we have groups of genes. And we can find the mapping between individual SNPs and individual genes by using R1 norm over here. And also we can find mapping between groups of SNPs and individual genes by using the R2 norm with SNP groups over here. And also we can find the mapping between individual SNPs and groups of genes by using the third penalty over here. So basically the idea is that we want to use the grouping information on SNPs and genes simultaneously to improve the statistical power of the GWA mapping. Here is the benefits of our model. by grouping SNPs, we can increase the signal-to-noise ratio of associated SNPs having small effects. Let's imagine this case. Here we have a SNP with small association strength, small effects. If you just look at this association, probably it will be difficult to detect this this association with small effect. But if we can group these groups with small effects, it will be easier to detect these groups of SNPs with small effects because the signal-to-noise ratio can be increased. So using the increased signal-to-noise ratio, we can identify SNPs having small effects on gene expression traits. And also by grouping genes, we can share information across different gene expression traits in the same group. Intuitively, if we saw an association between a SNP and a weak association between a SNP and a gene trait, it would be difficult to say that this is a true association with high confidence. But if we observe association between a SNP and multiple genes in the same group simultaneously, probably we can say that this is a true association with higher confidence. So this is the intuition, and in theory, it has been proven that by using this idea, we can decrease the sample size required for successful recovery of the matrix B. And this is here I briefly show the strategy of our optimization. We look at the block of the regression coefficients matrix, which consists of one input group and one output group. And this is the input of our pipeline. And in the pipeline, we first check whether this block should be 0 simultaneously by checking optimality conditions. If it is true, then we set it to 0, and we are done. But if it's not 0, we go to the second step, and we check whether each column of the block should be 0 together or not. And also we check each row, and also we check each element of the block to see if they should be 0 or not. And then a few number of regression coefficients will be non-zero. And for those non-zero regression coefficients, we update those coefficients to find the optimal solution. So basically, all these steps are designed to speed up our optimization, and we can actually very efficiently optimize our model. And also, we extended our model to include SNP-SNP interactions. And here we have additional terms over here, additional terms for SNP-SNP interactions. So for example, in this case, it represents the interaction between the SNP R and the SNP S. For this model, we first find the set R, which is the set of candidate SNP pairs for pairwise interactions. And this set R can be determined by using genetic interaction networks or pathway information. And in our experiments, we used genetic interaction networks to find the candidate SNP pairs for pairwise SNP-SNP interactions. And essentially, this model is the same as the previous model if we treat these interaction terms as additional terms in matrix X. So you can use the same optimization procedure to solve this problem. Now let me move on to the experiments. First, we perform the simulation to see if our model can use both grouping information on SNPs and genes. The goal is to find, and in our simulation, the goal is to find true non-zero elements in simulated known matrix B, and the data was generated by linear model with simulated matrix B, and this is the condition of our simulation. The details of the conditions are shown in our paper. And also we analyzed Yeast data, and the goal was to find SNPs or SNP pairs which affect expression levels of Yeast genes. And we, for data, we used Yeast genotype gene expression data from Bram et al. And we determined the SNP groups using genetic interaction networks and gene groups by applying M-code clustering algorithm to gene expression traits. And this is the result of our simulations. This is the precision recall curves when the true association strength was 0.2, and this is the precision recall curves when true association strength was 0.4. And here the precision was defined by this, and the recall was defined by this, which means that if we have high precision, then most of our findings are actually true. And if we have a high recall rate, then we found almost all, we found many true associations, SNPs. And this curve represents the results for our model. And this curve represents the results for the model with only groups of SNPs. And this curve represents the results with only groups of genes. And this curve is for Lasso. And this curve is for single SNP performed by Plink. If you look at the results, you can see that for both association strength, our model significantly outperformed other models, which means that given grouping information on SNPs and genes, we can improve the performance significantly. And also, if you look at these two models with only groups of SNPs and models with only groups of genes, these two models also outperformed Lasso because they could take advantage of the grouping information. But the performance gain was quite limited. But if we used both information simultaneously, we could observe significant improvement in terms of the performance. And also, we applied our model to Yeast eQTL data. And these are the hotspots that we found for SNP-SNP interactions. First, we found that these SNP pairs affect the gene expression levels of many genes. For example, the 11th hotspot affected more than 100 gene traits. And we also found that a group of genes affected by the same SNP pair have similar biological functions. For example, out of 11 hotspots, 9 of them had enrichment of Go category with significant p-value. And also we analyzed the hotspot number 1, which affected 455 gene traits. For this interaction hotspot, we found that there exists significant interaction between NUP60 gene and RAD51 gene with significant p-value. And also we found that these interacting genes were located nearby the two SNPs. For example, this NUP60 gene was located within the first SNP, and the second SNP was located within the gene RAD51. So it seems that these SNPs affected these two genes, and then the interaction between the two genes affected many gene traits. To conclude, The regression methods with penalties such as Lasso, group Lasso, and multitask Lasso can be used to address GWAS mapping problem. However, previous algorithms did not use grouping information on both SNPs and genes simultaneously. Our proposed methods showed promising results by taking advantage of grouping information on both SNPs and genes efficiently. And this is the future direction of our research. In human data, it is challenging to find biologically meaningful groups of SNPs and groups of genes. So first, we want to find grouping information for human data using many data resources. And then we want to analyze eQTL data for human diseases such as Alzheimer's disease using our model. And I would like to thank Seung Kim for very useful advice, and also CMU Sailing Lab. And also I want to thank ISMB 2012 Travel Fellowship. Thank you.